When a city's infrastructure fails, we are kind of conditioned to look for the spectacular disaster, right?
Oh, absolutely. Like a bridge collapsing.
Exactly. Or a massive water main bursting under downtown, flooding the streets. I mean, it makes the evening news the chaos is undeniable. And the root cause is immediately obvious to anyone looking at the broken concrete.
Yeah, the cause and effect are right there.
Right. But the far more dangerous threat to any complex system isn't usually the sudden explosion. It's the quiet, decades-long narrowing of the pipes.
The slow creep.
Yeah. Deep underground, the water pressure drops so incrementally that nobody even notices. You turn on the faucet, and maybe it takes just a fraction of a second longer to fill a glass. Meanwhile, the outer edges of the city are slowly starving for resources.
That is a perfect analogy for what we're talking about today.
Welcome to another custom-tailored deep dive.
Yeah.
We are exploring a phenomenon exactly like that slow plumbing failure today. But the city is your brain, and the hidden plumbing is the absolute key to understanding cognitive decline.
Our mission today is to really solve a classic chicken or egg mystery in neurology.
The ultimate brain mystery.
Right. So we know as a definitive fact that as human brains age, they lose white matter. The physical structural integrity just degrades.
But the lingering question has always been about the order of operations, hasn't it?
Exactly. Does the brain lose its white matter because the local blood supply fails? Or, and this is what a lot of people thought, does the blood supply shrink as a secondary reaction because the brain tissue is already naturally degenerating and, simply requires less fuel?
Right, like shutting off the power to an empty room. To get to the bottom of this, we're relying on a fascinating 2025 research paper published in Nature Neuroscience.
It's a fantastic paper.
It really is. It's titled, Impaired Capillary Venous Drainage Contributes to Gliosis and Demyelination in Mouse White Matter During Aging. And I feel like the surface level gray matter gets all the mainstream attention when people talk about keeping their memory sharp.
Oh, always.
Yeah.
Gray matter is the star of the show.
Right. But this paper zeroes in on the white matter, the deep, heavily insulated wiring connecting all those processing centers.
Yeah, specifically the superficial white matter, so the U fibers, which are situated just beneath our gray matter.
U fibers. I like that. It's easy to visualize.
Yeah.
Tiny U-shaped bridges.
Exactly. And they are critical for complex, rapid cognitive processes. The researchers actually used the mouse corpus callosum as an anatomical model for these human U fibers because the vascular architecture is remarkably similar.
So to understand why this deep wiring degrades, we basically have to look at the incredibly fragile way the blood drains out of it.
Yes, the plumbing.
Plumbing. If we're mapping the architecture of the deep brain, the arterial supply, the pipes bringing the good stuff in, is usually pretty robust, right?
Right. Arteries dive deep down from the surface to deliver oxygen-rich blood. They do their job well.
But venous returns the exhaust plumbing that clears the depleted blood out. That seems to be where a massive bottleneck happens. The researchers highlight a specific vessel, and we need to lock this term in, the principal cortical venule.
Or PCV for short.
PCV. So what makes the PCV so special?
Well, the PCV is basically the solitary hero of this deep drainage system, and that is precisely the problem.
Being a solitary hero is usually a bad design in biology.
It is. These are wide-reaching conical veins that dive all the way down into cortical layer 6 and the corpus callosum. The researchers mapped the entire ascending venous network and found something just staggering.
What did they find?
PCVs represent less than 4% of all the ascending veins in the cortex.
Wait, less than 4%?
Less than 4%. Yet they are almost entirely responsible for draining the blood from these deep white matter tissues.
Okay, let me just wrap my head around that. Less than 4% of the plumbing is handling the entirety of the deep tissue's exhaust.
Yeah, it's a massive structural bottleneck.
If I'm picturing the fluid dynamics here, it's not like a sports stadium with dozens of doors where you could just, funnel people out a different exit if one gets blocked.
No, not at all.
It's more like a massive watershed. Or actually a river delta running in reverse. You have thousands of tiny, low-pressure streams, the capillaries trying to force all their volume into one single, massive central river.
That reverse watershed dynamic is exactly what makes the white matter so vulnerable. To handle that sheer volume, a single PCV trunk has to be massive.
How big are we talking?
They average about 57.5 micrometers in diameter.
Which is huge for a brain vessel, right?
Right. A standard ascending venule in the upper cortex averages only about 19.8 micrometers. So a single PCV is supporting at least 8 times more blood flow than a regular vein.
Wow. Okay, so up in the gray matter, you have this dense web of redundant veins.
Exactly. If one gets sluggish up there, the blood simply reroutes through a neighboring pathway.
But down in the deep white matter, the PCV is it's a solitary exit point.
Yes. If the pressure dynamics change and those thousands of tiny streams feeding into it, the entire network backs up.
Let's do a quick recap here because we're about to dive even deeper. We've established that the deep brain wiring, the white matter, is drained by these massive solitary pipes called PCVs. They're basically the only exit door for the stadium.
Right. The bottleneck.
Which means we need to look at the tiny streams feeding that central river. If the PCV is the bottleneck exit, the actual traffic jams of aging must be happening in the narrow hallways leading up to it.
And that brings us to a very specific segment of the capillary bed. The paper calls them pre-convergence capillaries.
Pre-convergence capillaries. Let's create a mental image for this. They are the vulnerable middlemen, right?
Exactly. They are situated at the exact midpoint of the arteriovenous circuit.
So they are the furthest possible point from the high-pressure arteries pushing the blood in.
Right. And equally distant from the draining veins pulling the blood out. They sit right in the dead center of that pressure gradient.
Which means they naturally have the lowest blood flow velocity in the entire system. They're just barely moving.
Barely moving. Yet, according to the data, they make up 60% of the vessel segments in these deep networks.
Wait, 60% of the entire deep network is made of these slow-moving middlemen.
Yeah. There are a massive number of them, and they are barely moving any fluid.
I have to push back on the evolutionary design of this. I mean, if these pre-convergence capillaries are so vital for keeping our U fibers alive, why didn't we evolve redundant vascular loops down there?
It seems like a bad design, right?
It seems like an incredible oversight. Why trade vascular safety for a system this fragile?
Well, it looks like a flaw until you consider the biological economics of the skull.
Okay, meaning we only have so much room in there.
Exactly. The brain is housed in rigid, finite space. There is a brutal evolutionary trade-off between packing in dense neural wiring to increase processing speed and fitting in the vascular volume required to support that wiring.
So we have to choose between being smart and having safe plumbing.
Basically, yes. White matter is essentially a dense superhighway of thick myelinated axons. If you filled that space with redundant blood vessels to create vascular safety nets, you would have to sacrifice neural density.
We traded a robust plumbing system for higher intelligence.
That's a great way to put it.
So we are running a high-performance sports car with the thinnest possible fuel lines.
And as we age, those lines start failing. The researchers used in vivo 2-photon imaging, which is an incredible technology to look 1,000 micrometers deep into the brains of living mice.
Wow, looking into a living brain at that depth,
Yeah.
What did they see?
They saw what they call flow stalls, individual red blood cells just coming to a dead halt.
Like a traffic jam where everyone just turns off their engines?
Right. But if the baseline flow in these middlemen capillaries is already incredibly slow, you have to ask what actually causes the blood to stop completely.
Yeah, what's the actual roadblock?
They found a molecular smoking gun, an adhesion molecule called VCM1.
VCM1. Okay, let's give the listeners a memory trick. Velcro CAM1.
Velcro CAM1 is perfect. You can think of VCM1 exactly like biological Velcro that lines the inner walls of the blood vessels.
Okay, so in a young, healthy brain, is this Velcro active?
Oh, it's relatively inactive. The walls are smooth. But the imaging showed that in aged brains, specifically down in the corpus callosum, VCM1 expression is strongly upregulated.
The vessel walls become incredibly sticky.
Exactly.
So if the walls are sticky and the blood is barely moving anyway, the larger cells in the bloodstream are going to get caught.
Yes. And leukocytes, white blood cells, are larger and stiffer than red blood cells.
So if a big, stiff white blood cell comes drifting through this low-pressure, sticky hallway,
It gets caught on the Velcro CM1.
it just gets stuck to the wall.
Right. And it acts like a physical roadblock. The red blood cells pile up behind it and the flow completely stalls.
That is wild. How often does this happen?
The data backing this up is striking. They found that 92.5% of all observed blood flow stalls happen specifically in these pre-convergence capillaries.
92.5%. It's almost entirely happening right there in the middleman.
Yeah. And a stall isn't just a temporary inconvenience. When a capillary is blocked for an extended period, the surrounding tissue stops receiving oxygen.
And I'm guessing the tissue doesn't like that.
Not at all. It essentially signals that the vessel is no longer functional. This leads to what's called capillary rarefaction.
Rarefaction, meaning it just vanishes.
Basically.
Yeah.
It's the physical regression and permanent death of the capillary. It simply disappears, leaving the network even sparser than it was.
Let's do another quick recap. So far, we've got a solitary exit door to the PCV. We've got the slow-moving middlemen, the preconvergence capillaries. And as we age, sticky Velcro CAM1 traps white blood cells, stalling the flow and actually killing off those capillaries.
That's exactly where we are.
Okay, that explains the loss of overall network density. Capillary death alone doesn't explain what's happening to the vessels that do survive, right?
Right, there's another layer to this.
Because if a subset of capillaries dies, you might naturally expect the remaining ones to dilate, to widen up, and handle the redirected flow.
You would think so. But instead, the paper notes a uniform chronic narrowing across the surviving network.
So if the tube isn't blocked by a white blood cell, the tube itself must be physically shrinking.
Yes.
What on earth is squeezing these deep capillaries shut?
To understand that, we have to look at the mural cells that live on the outside of the capillaries, specifically the pericytes.
Parasites.
Right. Parasites literally wrap their tiny cellular arms around the endothelial tube of the capillary.
Like an octopus grabbing a pipe.
Exactly. They have contractile properties, meaning they can flex or relax to control the vessel's diameter. They are the gatekeepers of vascular tone.
So they operate like a hand gripping a garden hose.
Yes, that's a great visual.
A healthy parasite squeezes and releases to perfectly modulate the water pressure based on what the garden needs.
But the researchers found a severe drop-off in the parasite populations, specifically at the 800 to 1,000 micrometer depth.
Wait, let me guess. That depth is right in layer 6 and the corpus callosum.
Precisely where our PCD bottleneck is located.
Incredible. So what happens when the parasites die off?
Well, the loss of parasites at that depth creates a catastrophic chain reaction. You would naturally assume that if the parasite dies, the hand lets go of the hose and the capillary just remains permanently dilated.
Right, the muscle's gone, so the hose should pop open.
But biology is rarely that simple. The parasite dysfunction actually causes an abnormal, chronic constriction of the surviving capillaries.
So it's not letting go, it's clamping down.
It's as if a phantom hand is permanently gripping the hose, reducing the blood flow to a mere trickle in the deepest ports of the network.
That phantom grip gives us a highly quantifiable metric. Because of the VCM1 blockages and this parasite-driven constriction, the researchers measured a very specific drop in blood flow, didn't they?
They did, a highly specific 20% reduction in red blood cell flux in the deep white matter.
20%. We'll get back to why that specific number is so dangerous in a minute.
Yeah.
But what absolutely fascinates me about the hemodynamic mapping here is the phenomenon of blood shunting.
Oh, the Steele syndrome. Yes.
Because the upper layers of the brain, the gray matter, they didn't experience this 20% drop, did they?
No, they didn't. In fact, the upper cortex in these aged mice actually saw an increase in blood flow.
An increase, while the bottom is starving.
Exactly. It creates a dangerous redistribution. The blood entering the brain basically takes the path of least resistance.
Because the deep preconvergence capillaries are pathologically cramped and blocked with Velcro.
Right. So the arterial pressure just shunts the blood flow into the redundant venous networks of the upper layers.
So the rich get richer.
The upper gray matter becomes hyperemic. It gets way more blood than it needs, while the deep white matter is continuously, quietly starved.
That is terrifying. But if the deep vessels are clamped shut by this phantom grip, the natural question is whether that state is permanent.
Which is the million-dollar question.
Right, because if the pipes are calcified and hardened, like end-stage atherosclerosis, then therapeutic options are incredibly limited. There's not much we can do.
But the researchers tested this. They used a chemical called isoflurane.
Isoflurane. Isn't that an anesthetic?
It is commonly used as a gas anesthetic, yes. But on a cellular level, it acts as a potent vasodilator. It alters the ion channels in the cell membrane, effectively forcing contractile cells to relax their grips.
So they applied this to the aged mice.
They did.
Yeah.
And when they applied isoflurane, those deeply constricted capillaries dilated.
They opened back up.
They opened up. The red blood cell flux actually increased.
Wow. Which completely changes the narrative of brain aging.
It really does.
The plumbing isn't dead or permanently turned to stone. It is just pathologically cramped.
Exactly. If a chemical agent can force those parasites to relax and allow the hose to open back up, it means the physical structure is still viable.
We could theoretically design therapeutics to target that specific vascular tone, effectively unsqueezing the hose to restore blood flow to the U fibers.
It provides a very tangible, localized target for drug development. It's incredibly hopeful, but proving that the vessels can dilate doesn't quite answer our primary chicken or egg question from the beginning.
Right. Let's do our third recap to set up the grand finale. We've established the mechanism of the plumbing failure. We have a sparse PCV network. We have Velcro CM1 blockages in the middlemen capillaries. And we have parasite constriction causing a 20% drop in deep tissue blood flow.
All of that is proven.
But we still need to prove if this 20% drop is the absolute cause of white matter degeneration or just a symptom of dying tissue.
Right. And when white matter degenerates, the paper highlights two distinct pathologies that we need to understand.
Okay, let's break them down. What's the first one?
First is gliosis.
Gliosis.
Yes. This is where the microglia and astrocytes, which normally act as the brain's immune and maintenance cells, become chronically inflamed and essentially overreact. They start causing damage.
And the second pathology?
The second is demyelination. This is the physical stripping away of the fatty myelin insulation that coats the neural cables.
And without that insulation, the signals slow down, leading to cognitive decline.
Exactly. So to prove that the 20% blood flow drop directly causes these two conditions, gliosis and demyelination, the researchers utilized the UCCAS model.
UCCAS. UCCAS. What does that stand for?
It stands for unilateral common carotid artery stenosis.
Okay, that's a mouthful. How does it work?
Well, the researchers took healthy, young adult mice, pristine white matter, zero age-related cognitive issues.
Young, healthy brains.
Right. They performed a microsurgery to wrap a tiny, highly calibrated coil around one of the carotid arteries in the neck.
The main artery feeding the brain.
Yes. And by tightening this coil, they artificially clamped the main supply line.
Oh, wow. They engineered a precise mechanical chokehold.
Precisely. They calibrated the stenosis to induce the exact 20% drop in blood flow to the brain that they had observed in the naturally aged mice.
So they completely removed biological aging from the equation. They just recreated the plumbing deficit.
Exactly. They recreated the hemodynamic deficit of aging without any of the actual biological aging factors.
And what were the results from this young brain experiencing a 20% deficit?
The results are the definitive proof. The artificially induced hypoperfusion triggered the exact same microgliosis, astrogliosis, and demyelination seen in the older mice.
It triggered the exact same damage.
Yes. And furthermore, this damage was highly specific to cortical layer 6 and the corpus callosum.
The deep white matter.
Right. The upper cortex, which still had relatively better flow due to its redundant vessels, was spared.
That is incredible. So the plumbing failure is definitively the egg. The brain damage is the chicken.
We solved the mystery. Blood loss causes the brain to shrink, not the other way around.
But I have to pause on the severity of a 20% drop.
Okay, why?
Because a 20% reduction in anything usually implies a functional margin of error. Like, if my paycheck drops by 20%, I definitely have to budget, but I don't starve to death.
Right, you make do.
A stroke is an acute 100% blockage where tissue visibly dies in minutes. Why is a seemingly mild 20% drop have the power to strip the insulation right off our neural wiring?
It's an excellent question. The lethality of a 20% drop really comes down to the unique metabolic demands of the specific cells that manufacture that insulation.
What are those cells called?
Oligodendrocytes.
Oligodendrocytes, the myelin builders.
Yes. They are the cells responsible for wrapping and maintaining the myelin sheath around the axons. And they are incredibly energy intensive.
They eat a lot of fuel.
A massive amount. Maintaining that vast network of lipids requires a massive, uninterrupted supply of oxygen and glucose.
But they live in the deep white matter.
Exactly. The researchers note that because the blood has to travel so far down into the gut tissue, by the time it reaches those pre-convergence capillaries, the oxygen pressure, the PO2, is already naturally sitting at the lowest viable baseline.
So the oligodendrocytes are already living paycheck to paycheck just based on their geographical location in the deep brain.
Yes. They have no savings account. So when you reduce their supply by another 20%, The PO2 drops below their metabolic threshold.
They simply don't have the biological currency to maintain the myelin anymore.
And that marginal drop is what makes the whole process so insidious. The tissue is literally starving, but the 20% reduction is mild enough that it completely bypasses the body's natural emergency hypoxia alarms.
Oh, wow. So if it were a full-blown stroke?
The acute lack of oxygen would trigger massive inflammatory and rescue cascades. Sirens would go off everywhere.
But because the oligodendrocytes are just slightly underfueled?
The system doesn't realize it's in danger. The tissue just quietly, chronically degrades over years and decades.
The silent narrowing of the city's pipes.
Exactly.
If we pull back and look at the macro implications of this microscopic bottleneck, the so what, for anyone listening, is profound.
It really is, because the degeneration of these superficial white matter U fibers isn't just a mouse problem.
No, it maps directly to us. It is a primary driver of cognitive decline in major human conditions: Alzheimer's disease, multiple sclerosis, and cerebral small vessel disease.
By identifying the PCV bottleneck and the parasite constriction, science now has a physical, identifiable mechanism to treat.
It entirely reframes how we view the timeline of cognitive decline.
It does. If we can intervene early to keep those deep capillaries dilated, maybe using principles similar to the isoflurane experiment, or develop therapies to prevent VCM1 from trapping white blood cells,
We could theoretically protect those oligodendrocytes from starving.
exactly, and halt a major mechanism of white matter aging altogether.
Which just reinforces the oldest, truest cliche in neurology, doesn't it?
Cardiovascular health is brain health.
Every single thing you do to keep your arteries flexible, to manage inflammation, and to maintain a healthy blood pressure, it is directly supporting the flow dynamics of those tiny, vulnerable preconvergence capillaries deep in your white matter.
Blood flow is cognition.
When you protect the plumbing, you protect the wiring.
The physical mechanics of the vascular system literally dictate the lifespan of the neural system.
So since this entire deep brain ecosystem relies on incredibly fragile structural bottlenecks like those PCV exit doors, I want to leave you with a final thought to mull over.
Okay, let's hear it.
If a mere 20% shift in flow dynamics over decades is enough to quietly starve your white matter, consider the physical mechanics of your daily life.
Oh, like habits.
Yeah. Think about chronic, low-grade dehydration subtly thickening the viscosity of your blood year after year.
Making it harder to push through the middleman capillary.
Exactly. Or consider something as constant as gravity and the physical positions we sleep in night after night for an 80-year lifespan.
That's a fascinating point.
Do these daily, repetitive micropressures slowly turn the wrench on the brain's hidden plumbing? Are we slowly altering the fluid dynamics of those deep exit doors just by how we exist in physical space?
It really makes you rethink your daily habits.
It's definitely something to think about the next time you turn off the lights and settle in for the night. Thanks for joining us on this deep dive, and we'll see you next time.